When a traditional network router attempts to process 100,000 packets per second, the architecture hits a physical geometric limit. Engineers identify this failure state as the memory cliff. It occurs when data loads exceed the capabilities of legacy static memory partitioning. In these systems, data is written to fixed physical RAM addresses. Under extreme loads, the CPU cannot clear the buffer as fast as new data arrives. This chart shows the empirical ablation logs from the Prime V1 hardware tests. At 100,000 packets per second, routing latency reaches 45 milliseconds, while peak throughput stalls at 450 gigabits per second. The buffer overflow rate exceeds 5%. During this failure, memory utilization reaches 92%, leaving no overhead for processing recovery. The Prime V2 M1 proxy utilizes a different coordination algorithm. In the same test conditions, latency drops to 0.15 milliseconds, and throughput increases to 1,280 gigabits per second. The overflow rate is reduced to 0.0002%. Scaling up physical RAM capacity does not address the underlying Euclidean geometric bottleneck. Removing these constraints requires a different mathematical foundation for routing. Stability at terabit speeds involves moving away from centralized, state-locked memory addressing. The R4 Prime router uses a non-Euclidean geometric manifold mapped natively to local CPU caches. This shift replaces hardware dependency with topological coordination. Standard hardware clock speeds cannot reach 1.2 terabits per second. That throughput requires a structural change to the geometry of the network substrate itself. Standard TCP/IP routing tables rely on two-dimensional meshes. In a Cartesian coordinate grid, linear data vectors move along x and y axes. This leads to inevitable intersections at centralized nodes, resulting in bottlenecks. The R4 architecture utilizes a hex hive modulo 6 topology. This structure allows parallel tracks to curve past each other in high-dimensional space. The system maps physical node interfaces onto coordinates defined by the distribution of prime numbers. By establishing parallel channels at distinct prime coordinates within the same residue class modulo 6, the system ensures these paths never naturally intersect. The arithmetic distance between these channels prevents data overlap. Projecting continuous coordinates onto these discrete prime indices eliminates coordinate drift. Guiding data across this curved topology requires more than just static coordinates. The R4 router uses a continuous coupled field approach. The formula balances discrete graph adjacency with continuous hyperbolic distance to create a dynamic potential field. A coupling coefficient weights these two mathematical environments to guide the packets. To maintain stability, the sum of the manifold's Ricci curvature and the Hessian of the potential field must remain strictly negative. Ricci curvature describes the spatial deformation of the manifold, while the Hessian represents the variance of the potential field. Maintaining a negative value for this sum drives the network toward deterministic convergence. Chaining these updates to Liouville's conservation laws and the contraction mapping theorem prevents parameter drift. This combination of discrete adjacency and non-Euclidean physics provides systemic stability under extreme data loads. Standard linear attention gates scale quadratically, meaning memory requirements increase exponentially as the network grows. Hopf angular routing, or HAR, is designed to bypass this scaling limit. HAR projects high-dimensional input vectors onto compact 3D stereographic Hopf circles. State updates are computed by evolving these coordinates in log space using a Levi-Civita phase transport correction. The R4 model replaces standard neural network weights with 16 interlocking orbital rings. The frequencies of these rings are derived from the imaginary parts of the non-trivial Riemann zeta zeros. Data packets traverse these rings like a wave murmuration, adjusting their states relative to immediate layer 2 neighbors. This projection achieves a sublinear scaling law. As the network grows, the router becomes more efficient relative to its size. Executing these geometric operations on local hardware, like the Apple M1, requires mapping non-Euclidean math directly to the CPU cache. Phase-based continuous buffering replaces the practice of writing to fixed physical RAM addresses. The Predictive-Buffer algorithm preemptively forecasts packet routes before the CPU requests them. This prediction is based on the localized structural curvature of the geometric manifold rather than past traffic history. In practice, this results in a 97.4% CPU cache hit ratio. This accuracy decouples memory allocation from sudden CPU spikes. By anticipating the required local vectors, the algorithm suppresses synchronization overhead to 0.15 milliseconds, suppressing latency spikes. These principles apply beyond local hardware to massive enterprise cloud networks. PrimeOS is a Rust-compiled Internet operating system that virtualizes this routing stack. PrimeOS models physical hardware constraints, such as thermal saturation and electromagnetic noise, within the routing stack to maintain stability during high-load events. The system runs hologram containers as pure virtual private infrastructure. This architecture allows for state migrations across heterogeneous cloud environments without traditional physical tethering. Running on these geometric rules delivers a 3x compute performance increase compared to standard CPU baselines. By utilizing geometric workload routing, this system elevates active infrastructure utilization from the legacy average of 15% up to 95%. Solving the routing problem addresses the power and thermal limits that often bottleneck multi-agent AI networks. In this system, data compression and selection are not programmed at the application layer. These functions arise from the underlying physical information dynamics, where data follows the path of least resistance across the manifold. Empirical logs clearly show that flat Euclidean architectures face severe scaling constraints in high-dimensional coordination that non-Euclidean structures simply do not. The scaling of artificial intelligence is no longer bound solely by hardware expansion, but by the topology of the network itself.